My name is Aaron Bembenek, and today I'm making the claim that Datalog-based systems can use incremental SMT solving. In prior work, we've interfaced Datalog with external SMT solvers because we're interested in static analysis, and both are great tools for writing static analyses. When we were doing this, we faced the practical challenge of how we could take advantage of incremental SMT solving, which is important for performance. This is an issue because, at least at first blush, standard Datalog evaluation does not generate SMT queries in a way that would lead to good incremental solving. To get around this challenge, we explored the potential solution of adding a layer between the Datalog engine and SMT solver that uses tricks from the formal methods community to encode SMT assertions in clever ways. And we found that this can consistently lead to speedups over the non-incremental baseline. In fact, our best strategy led to a speedup 75% of the time during our experiments. In this work, we focus on Formulog, which is a language that combines Datalog and SMT solving. In Formulog, you represent SMT formulas using complex terms, and then you can use built-in operators to take one of these complex terms and send it off to an SMT solver to ask questions about it, such as whether that term, interpreted as an SMT formula, is satisfiable. You could use Formulog to represent and reason about proposition graphs, which are graphs where the edges are labeled with SMT propositions, like the graph on the slide here. To do this, you could declare an EDB relation, and then go ahead and enumerate the members of that relation, where the third argument for an edge is going to be a complex term representing an SMT proposition. Once we have this graph, we could go ahead and do some sort of computation on it, such as computing reachability modulo path satisfiability, where we're saying a node is going to be reachable only if the path leading to that node, if you take all the constraints along that path and make a conjunction of them, that conjunction has to be satisfiable. So how would we do that? Well, we could declare an IDB relation reach, define a base case for that relation saying that entry point 1 is reachable, and then define a recursive rule. The logic we have here is very similar to what you'd have for something like doing graph transitive closure in Datalog, except that we have these logical terms floating around, and we invoke the operator isSat, which is going to be making a query to an external SMT solver. It turns out that if you run this computation, Formulog evaluation is going to simulate breadth-first search. So what happens? We start at our entry point, and we'd explore the edge to 2, generating the constraint x is less than y. We'd then explore the other edge from the entry point, generating a different constraint. We'd go back to where we were before and try to explore the edge from 2 to 3, generating the constraint x is less than y and x is equal to y. And then we'd go back to the fourth path and generate a different constraint there. The issue is that breadth-first search is not obviously a good match for incremental solving. And this is apparent from the fact that, in our example, no two consecutive queries share conjuncts, which means that we'd have to reset the solver state between each call, which is bad for performance. And this is despite the fact that there are shared conjuncts, but they're just shared between every other call. Our solution to this is to add a mechanism that sits between the Formulog runtime and the SMT solver. This mechanism is pretty simple and just has a few key ingredients, such as fresh Boolean SMT variables, logical implications, and the SMT lib command check stat assuming. Now let's go back to our example. When we explore this first edge, we're going to assert to the solver that A implies x is less than y, where A is some fresh Boolean variable, and then we'll ask the solver to check satisfiability assuming A. And we'll do something similar for our next edge. Then when we go back to the first path we were exploring and try to extend it, we'll assert to the solver that C implies x equals y, where C is a fresh Boolean variable, and we'll check stat assuming both A and C. So here we're reusing an assertion we made previously to the solver, and we'll do something similar for our final path. So note that we aren't resetting the solver between calls, which means that we should be able to get some incremental solving here. We wanted to test whether this strategy works for Formulog in practice, and so we compared it against a baseline strategy that uses no incremental solving and an alternate strategy that uses the smtlib push and pop commands. We tested these strategies on 3 Formulog benchmarks and across multiple SMT solvers and smtlib logics. Our results show that the strategy based on checkstat assuming is by far the best. In our experiments, it had a speedup over the non-incremental baseline 75% of the time. In comparison, the strategy based on push-pop only had a speedup 37% of the time. In future work, we want to explore the question, how much does the data log evaluation algorithm actually matter? That is, assuming that you're using one of these strategies, how much does the data log evaluation algorithm you use actually affect the amount of incremental SMT solving that happens? With that, I'll conclude and just leave up this slide with some more detailed results. Thank you.